Alright, morning everyone. Just still untangling stuff. And we're in. Alright, clinics. Remember there's a clinic straight after this if anyone needs a clinic, and every other day at noon. Quiz redemptions, yeah, A4 by Friday. That's just a general note that for any of your worksheets, if you miss a tutorial or if you just have want blank versions, they're behind the door in the maths drop-ins, or there's always blanks and solutions on Blackboard. Put out an announcement already, but that's just a general announcement. So we've got the mid-semester exam a week from today. So it'll be in this lecture. If you've got an AIP and you've sent it to me, I've emailed you to talk about an alternate room than this one. If anyone else has got an AIP and you think you haven't sent it to me or you have other requirements, just email me, okay? Let me know if there's other issues going on and we'll sort out. But the normal exam will be 90 minutes worth here in a week. 30% of assessment, yes, the resource sheet, two-sided, front and back, handwritten. Revision papers on Blackboard put up Friday, and the answers are up. Online adverse circumstances. If you miss this one or if you're going to miss this one, there's also someone else who's going on holidays. They're sitting it early. That's been sorted. But if anyone's got other issues, just, again, let us know if things aren't going to happen. Or if you're Crook next week. If you sit at Crook, that unfortunately at uni we don't have a situation. This goes for any of your major exams. Don't sit at Crook. Or, you know, unless you think, yeah, I'm fine, look. Because you can't sit at Crook and then apply for adverse circumstances. If you're Crook and not going to get what you should, skip it. And then put in order adverse circumstances and apply for late sitting, okay? Best way to go about it. Apart from that, any general questions at the moment? Go on. It's in order, A1 to A6. It's just, there's 6 questions in the mid-term, and questions 1 to 6. Lecture 1, Lecture 2, Lecture A3, yep. Totally in order. Even the questions are in order, I'm pretty sure, of within topic. So some people might do a resource sheet that is totally, you know, 6 sections of the resource sheet, so you know where you get heading to. Yep. Any others? Oh yeah, sorry, Taylor. Nope. Oh, that's the other thing. Let's mention that. Yeah, next week there's no maths shoots, no little quizzes. Next week the only thing maths-wise is this, and there's no lecture. It's just come here for the mid-semester. That's it. Make sure you bring a calculator. Know how to use it in stats mode. I'll have a couple of spares, but not necessarily the one you're used to. Yeah. Any others? But yeah, the revision paper is set out just like yours will be. All right, cool. So this week is not in the mid-semester, and this week's is not tested next week in a little quiz. Its little quiz, the marks are not going to be good, is the first week back after the break. Because obviously next week we had the mid-sem, then we've got 2 weeks off, and then as soon as we come back, the little quiz on this stuff. So with 2 week off brain, ouch. But at least we know, yeah, we get a little quiz on everything. This one's just going to happen in week 9. But this week's we still did the standard little quiz on last week, and we discussed this stuff. And if last week was going okay, what we ended up last week, we just, last week was all blogs and stuff, and then at the end we just said, well, how do I solve for the power if it's horrible? If it's 5 to the x equals 30. I know 5 squared is 25, I know 5 cubed is 125, 5 to the x equals something else. That little technique we're going to use a bit today. So today's still a revision on that. Apart from that, I think you'll find exponential functions not too bad. Let's get in and find out. We start theoretically. We did in week 5 just look at the general shape of an exponential function. And we didn't go much into it. We just looked at the rough shape like we did a few things. If we look at that one, y equals 2 to the x. If I was to plot that, again, we don't have to plot these things. This is just something we're doing just to say, look, I know roughly, I know why it looks like that. Well, 2 to the minus 3, the calculator will tell me, is 1 over 2 cubed, which is an eighth. 2 to the minus 2 will be that. 2 to the minus 1 will just be that. Anything to the naught is a 1. Anything to the 1 is itself. 2 squared is 4 and 2 cubed is 8. So there's some points. Let's plot them. A minus 3 is only as high as an eighth, right down here. Minus 2 is only a quarter. Minus 1's a half. Naught is up at 1. 1 goes to 2. 2 goes to 4. And 3 goes to 8. So there's our first exponential sort of thing. And yeah, we can see as we move, every step we go along from left to right, it just keeps getting times by 2. Okay? An eighth became a quarter, a half, just constantly times by 2 every step we go along. That's exponential stuff. There's always some multiplier. It won't always be 2. It might be times 3, times 10. Sometimes it'll be times a half, but it's just constantly timesing by the same number. And they just look like y equals some number to the x. And that number is what it's being times by. Okay, it's clear when I look at y equals 2 to the x, I can see that everything keeps getting times by 2. Every time I raise x by 1, it just chucks in another times by 2. So, okay, that's what one looks like. There's an example in an applied sense. It could be just a population that keeps doubling every day, every month, every whatever. So here, this population started at 2, then became 4, 8, 16, 32, 64. Yep, exponential growth. It could be exponential decay. So we just call it growth if it's going up and decay if it's going down. Doesn't mean it's necessarily, you know, some radioactive material decaying. Decay just means it's getting smaller. Okay? You see here that everything keeps halving. So if I was looking at the function of that, instead of being something like y equals 2 to the x, it's going to be something like y equals a half to the x. Okay, this number still tells me everything I need to know about it, as in whether it's going up or down. If it keeps getting times by 2, it's getting bigger. If it keeps getting times by a half, it's going smaller. This one keeps getting times by a half. It used to be 64, then 32, then 16, then 8, 4, 2. All right, exponential growth going up and exponential decay coming down. Something they've got in common, just what I've got in the box there, is that when x is 0, y is 1. So if it's y equals 2 to the x, 2 to the 0 is 1. That's our probably strangest power thing, and the calculator will always back us up on it. But no matter what we stick in the calculator, 16 to the 0, 7 to the 0, whatever, you always get 1. So in the same way, whether it's exponential growth or decay, if I said what's a half to the x, and x was 0, a half to the 0, it's still 1. So whether it's going up or whether it's going down, these things continually pass through a y-intercept of 1. So the other slide is this one. Okay, the scale is different, but it's just saying they still pass through when x is 0, y is 1, no matter what. So there's something in common. They both pass through a y-intercept of 1. Some go up, some go down. The basics of it is, and hopefully it'll be a common sense thing, if that number is greater than 1, it's increasing. Okay, if you times constantly by a number that's greater than 1, you've got to get bigger. Even if it's just like y equals 1.00001 to the x. Imagine if that was our function. Ignore that second dot there. Is that greater than 1? Yep, not much, but it's increasing. It's a tiny amount. If you keep timesing by 1.00001, it's increasing. Anything greater than 1, but if I times it by even just 0.9999, that's decreasing very slowly, but it's going downhill. So that's always saying this number is either bigger than 1, which is growth, or it's less than 1, which is decay. We're not interested in what if A is 0 or A is negative. Let's first look at the A equals 1. I didn't mention A equals 1. I said, what if it's greater than 1? What if it's less than 1? What if it was equal to 1? Just y equals 1 to the x. You don't think what that'll look like? It's just going to flatline. If y equals 1 to the x, 1 to any power is still 1. Okay? 1 to the power of infinity is 1 by 1 by 1. Yep, it's all 1s. So that's the middle line. Y equals 1 to the x. And that's actually going to be useful for us because we can look at that and say, well, if y equals 1 to the x, a flat line, anything higher is going to look like that. That might be y equals 2 to the x. If it's less than 1, it might be this one. y equals 0.9 to the x. I know I like to think that y equals 1 to the x is slap bang in the middle, and I'll get growth from that, and I'll get decay under that. There's another slide coming up like that. And this one's just nerd stuff. Why are we ignoring a is less than 0? If say I had an a that was negative, how would that graph? Well, it graphs like that, and that's not helpful for us. We're just looking at good old exponential growth, something that models real life, population of rabbits, people, whatever, radioactive decay. That graph isn't useful for us, so we're just leaving it. Same as last week with logs, we didn't look at negative bases. This week, it's the same thing. We're not looking at negative values of a. So it's just not for interest with us. So here is what I'm saying, that let's look at the steepness. If that's y equals 2 to the x, just a sketch, yeah, that might be something that just keeps doubling. Well, y equals 10 to the x will just be steeper, but they've got the same y-intercept, because whether it's 10 to the naught or 2 to the naught, it's still cutting at 1. And y equals 1.5 to the x, it's still growth. It's just not as steep as 2 to the x or 10 to the x. So we've got certain questions where we just want to order them. Say, given that y equals 2 to the x is in the middle, would green or blue be y to the 10x? Hopefully, looking at that, the logic is clearly green would be the y equals 10 to the x, if it's steeper. And again, just look, even though it might seem clear, if y equals 1 to the x is the flat line, then it goes 1 to 1.5 to 2 to 10. Yeah, all those numbers are increasing. Fair enough. What about if they're decay? If that's y equals 1/2 to the x, something that kept or your direction, kept halving as every time it got smaller, y equals 1/4 to the x would be steeper. Now that I think could be confusing. Hang on, shouldn't 1/4 be flatter? Should 1/4 really be steeper than that? Well, look at the logic. I'm saying if 1/4's are really steep and half's there and 3/4 is there, to me it makes sense if I think, well, y equals 1 to the x is a flat line. So the closer to 1 it is, the closer to this dotted line it is. So this barely, oh, that's horrendous. Something that was really flat, yeah, it's decaying, but not by much. Maybe that's 0.99 to the x. Okay, so to me, if I was being asked to rank them, I would see that the number closest to 1 is closer to flat. The further away it gets from 1, the further away it gets from flat. So 1/4 of the x is incredibly steep. 3/4 is not so steep. So we've got symmetry going on there. Just think y equals 1 is flat and the rest are close to it, but escalating. So, and you'll see soon an example of what's it going to do to us here. An example. But we've got to introduce something else first. And it's the last thing we're going to introduce in this exponential stuff. Soon will be more repeating last week. Sometimes there is a number out the front. We had like 2 examples at the end of a worksheet last week where I was trying to stress that this will happen. Say we had, what was one of them? I can't remember any actual examples. Say it was 60 equals 5 times 3 to the x. And what I was trying to avoid was, don't do the 5 times 3. We're not allowed to do that yet. Auto operation says no, but I can divide both sides by 5. And we're saying that that's the better way to do. Divide both sides by 5. That's an easier equation to solve. So what we're introducing is the fact that sometimes there will be a number out the front there, especially this week. So here we're saying, okay, what if there was a number out the front? Well, if that's y equals 2 to the x, let's look at what would happen if we stuck a 2 out the front. If the equation was, remember that's still a times, y equals 2 by 2 to the x. Again, that's not the same as 4 to the x. I can't do that yet. I've got to do my power first. Well, what happens? Well, if 2 to the x was just these numbers, all that's going to happen is all those numbers just get times by 2. So 2 to the naught was a 1. Well, now, instead of being 1, it's a 2. 2 to the 1 was 2, now it's a 4. 2 to the 2 is 4, now it's an 8. Everything just gets doubled. So y equals 2 to the x might look like the red one. Y equals 2 by 2 to the x just looks like the green one. So the y-intercept has changed. It just got times by 2. So instead of cutting at 1 like the red did, it cuts at 2. And looks a bit steeper. Okay, so what we've got to accept there is that sometimes there's a multiplier out the front. Now the y-intercept of this line, it cut the y-axis at 1, which does look a bit odd because, hang on, where's the 1? 2 to the naught is 1. It's nice to think of y equals 2 to the x. It's like it's y equals 1 times 2 to the x, because that's still true. And I can just say, whatever this number is my y-intercept. So if you ask me about y equals 1 by 2 to the x, I can look at that and see my y-intercept is whatever number's out the front, and it keeps increasing by whatever this number is. Start at 1 and keep timesing by 2. If I ask to look for this one, it's got a y-intercept of 2 that keeps timesing by 2. So we'll see the pattern. What about y equals 5 by 2 to the x? Well, its y-intercept will be 5, but it's still getting times by 2. So it's going to be 5, and then 10, and then 20, and then 40. So there's the next one. So look at those patterns, okay? The y-intercept is whatever's out the front. And y equals 2 to the x I can think of as like it had a 1 times out the front. Y-intercept of 1. So here's the sort of thing. Let's look at these patterns and think, well, okay, y equals 2 by 4 to the x. I'll come back to that one. The first thing I'm thinking is that number there is going to be the y-intercept. And that 4 tells me it's going up. It's a growth. Y equals 0.8 to the x. What number's out the front? Well, it's like there's a 1 times. Same with this one. If there's nothing there, it's like a 1 times. Is this growth or decay? Well, it's 2 to the x. Keeps timesing by 2. That's going bigger. This one's only 0.8. It's less than 1. This one's getting smaller. Y equals a half to the x. It's still like there's a 1 times out the front, and a half is less than 1. So I've got 2 growth ones because of a 2 and a 4 being greater than 1. I've got 2 decay ones because of 0.8 and a half are both less than 1. 3 of them have y-intercepts of 1, and 1 of them has a y-intercept of 2. So to me, B is instantly green. B had a y-intercept of 2 and it was growth. Y-intercept of 2, growth, B had to be green. Now there's only one other increase with a y-intercept of 1. The only other increasing function apart from B was A, y equals 2 to the x. So that's B. That must be A. So that's y equals 2 by 4 to the x. That's y equals 2 to the x. The other two both have y-intercepts of 1, 1 times, 1 times. Here I've just got to work out, and they're both decay, which one should be steeper. And in my mind I'm picturing old flatmate. And I know the flat line is just 1 to the x. Which one's closer to that, C or D? 0.8's closer to 1 than half is. So this must be the y equals 0.8 to the x, and this must be the y equals a half to the x. So yeah, if that's a half, 1 to the x, that'll be the 0.8 to the x, that'll be the 0.5 to the x. Yep, they're in order. 0.5 as in the half. So it's just y-intercepts and growth or decay and how steep. That's our exponential graphs. That's as far as we go with them. We're not bothering with any that are flipped. We're not going to put a minus out the front and suddenly look at them down here because we're interested in just normal growth and decay. Okay? No flipping, nothing fancy, just them. So with that intro, and that doesn't mean we've left it, we're going to keep seeing it, okay? That's the intro, but we're going to go into construction exponential function, and you'll start to see we're going to repeat what we just learned. So if an exponential function is of that form, now previously we were just talking about y equals ka to the x. All we're doing here is getting a bit applied, which makes life so much nicer when you start talking about real life a bit more than just x's and y's. What that's saying is some amount A is equal to this A0. Whenever you see that, you'll see that heaps in science. You probably already are seeing it in physics. When you do that, that just means initial amount. That's like saying when t equals 0. So it's not to the power of 0. That would be up here. It's not a superscript, it's a subscript. So A0 just represents the initial value of A. So if we get a picture, the amount after time t, if it's given to us by this formula, A equals A0 m to the t, let's look at what each bit means. A0 is always the initial amount. Think of it as a y-intercept. The initial amount sits right there. What amount was it at the start? That, wherever it touches the y-axis, that's where it starts. Because I'm not interested in negative time. It starts there. And then it gets multiplied by some m. Maybe it's 2. Maybe it's doubling. I don't know. But I've got some initial value, which is the y-intercept, and it keeps getting times by something. Maybe it's going up, maybe it's going down, but that's all we care about. I'm not interested in that side of it, because negative time just doesn't interest me in a practical situation. And the t is the time. Maybe it's days, maybe it's years, we'll get told. It doesn't matter, it's some form of time. So we've got an a-axis, so this could be the amount of radioactive material left after a certain amount of time. And maybe it says we started at 50 grams and then it kept halving. So it might be that graph. Okay, the 50 goes here, so maybe it was the amount is equal to the initial amount 50. That would be the graph for it. I'm starting at 50, and after every time, every month, every second, every whatever you define it as, it keeps getting times by a half. So after one, let's call it hours, it's only 25. After 2 hours, it's 12.5, and so on. Leave that. So, if I was talking about an initial value of 10, whatever it is, just the number 10, being repeatedly multiplied by 2, that's how I'd set it up. Initial value goes in the front, multiplying factor goes there. A equals 10 by 2 to the t is just a 10 that keeps getting times by 2. When t equals 0, we know that 2 to the 0 is 1. When t equals 0, a is a 10. Well, that's why it's its initial value. When t equals 1, it's 10 by 2 to the 1, which is just 10 by 2, which is 20. When t equals 2, it's getting times by 2 twice. It's the same as this number times 2. So hopefully the formula makes sense, that a equals 10 by 2 to the t starts at initial value of a and keeps getting times by 2 every time you increase t by 1. Okay? That's exponential growth, starting at 10 and getting doubled. What if it was only, and there's the graph, starting at 10, continue to increase. What if it was only getting multiplied by 1.2? It's not quite as steep. Still the exact same thing going on. We're starting at 10, there it is, and it gets times by 1.2 to the t. So when t is 0, it's just 10. When t is 1, it's been times by 1.2. When t is 2, it's been times by 1.2 twice. T is 3, so that formula is totally, it's not as steep. But every single one of these things has the same format. Initial and a multiplying factor. So let's work out, what are we really doing? If I'm multiplying by 1.2, maybe I'll just get told to multiply by 1.2, but more likely, what's really happening? If I'm timesing something by 1.2, it's the same as saying times by 120%, which means I'm making it bigger than what it used to be. A times 100%, that's just doing nothing to it. That's like timesing it by 1. That's just saying A times 100% is just being itself. What am I really doing when multiplying by 1.2? I'm increasing by 20%. So every time I times by 1.2, all I'm doing is the 1 represents its whole value, the 0.2 is how much it's going up by. So do these things make sense? If I'm increasing by 20%, I want to times by 1.2. Increase by 30%, I want to multiply by 1.3. Increase by only 5%, I'm times by 1.05. So the tempting thing would be, if I want to increase by 20%, times by 0.2. But if I times by 0.2, I'm making it really, really small. If I want to do nothing, I'll times by 1. So that's why these things increase by 20%. You've got to have the 1 to keep the value it was. The 0.2 is the 20% increase. The 1 is what it was, but the 0.3 is the increase. And how did I get 0.05 out of 5%? Well, it is just 5%, which is 5 divided by 100, which is 0.05. Hence, the 1 is what it was. Increase it by 0.05. So we'll have questions that says stuff like, this thing is going up by 10%, times by 1.1. In other words, 110%. something's increasing by only 1% times by 1.01, the 1 plus the 1%. So which of them? If something's increasing by 2% per day, so you want to times it by something which increases it a bit, it can't be A. For starters, A is talking about 20%, but that makes it small. B is sort of okay, but again, that's referring to 20%. C, that's making something really small. There it is there. If I'm increasing something by 2% per day, 1 is the amount that does nothing to it. 2% is the same as 0.02, so I'm timesing it by 1.02. So a question would say, if you're increasing by 2% per day, it expects you to know, well, I better times it by 1.02. What if we're multiplying by 0.8? We can see it's getting smaller. If we're timesing by a 0.8, it's less than 1. How much less than 1? Well, let's look at this. Timesing by 0.8 or 80% is the same as timesing it by itself, or timesing it by its full amount, minus this much. So what this slide is trying to get at is if you're timesing by 0.8, what are you really doing? You're decreasing A by 20%. So the question says, I want you to continually decrease an amount by 20%. You've got to think, well, 20%, that's 0.2. If I want to decrease amount by 0.2, well, it's 1 minus 0.2. Timesing by 0.8 does exactly that. So to decrease an amount by 20%, I've written it both ways. Some people prefer thinking decimals, some people prefer thinking percentages. But just think if it's decreased by 20%, take it off the 100. Decreased by 30, take it off the 100. By 5, take it off the 100. And all these is the percentages converted to decimals, which is always divided by 100. So I hope there's some common sense there that, okay, increase it by 50%, I'll times by 1.5. Decrease it by 50%, I'll times by 0.5. I'm either adding to or subtracting from 100%. Another example. This one's, a bit of a trap, but it's that exact same logic. If I want to decrease by 60% per day, I want to times it by something which keeps making it 60% smaller, I want to compare it to 100. Times by 100% does nothing, no change. If I want to reduce it by 60%, let's take 60% off that. 100 minus 60% times 40% is exactly what we're saying. You times something by 40%, you've dropped it by 60. And which of them is equivalent to timesing by 40%? It's that one. It can't have been that or that. They're increasing. You times by 1 point something, you're making it bigger. I wanted to make it smaller. And I can understand that that might look tempting, but decreasing by 60 means take it off 100. So we're either adding to 100 or taking it off 100. If I change this question, what would be the multiplying factor for increasing by 60% per day? Well, instead of subtracting the 60% to get that, I would have added the 60%. In other words, I would have times by 1.6. So increase by 60% times 1.6, decrease by 60% times by 0.4. And this one is just when we get, it's exactly the same, but 0.5% just tends to cause issues. Trust your calculator, it's all good. If I'm doing this here, I'll think for the same method as we said on the last slide. I'm always going to do something to 100%. I want to increase, so it means add it. 100% plus 0.5%, well, that is, I want to increase it by 100. That's what I want to times it by. What's 100 plus the 0.5%? 100.5. So what's that as a multiplying factor? Again, any percent divided by 100 gives you your multiplying factor. So divide by 100, or just trust your calculator, is 2 moves smaller. Okay? That one. Again, it might have looked a bit, I don't know which one. But every single percent, if you can say increasing means add it, 0.5 to the 100, but if you want a multiplying factor, divide by 100, that's it. Don't overthink it. So here's a precise example. Where's all that heading, and where's this repetition you were talking about, so we can make sense of it? Let's try it here. Construct exponential equations for each of the following scenarios. Okay, an initial value of 100 being increased by 6% every day. Well, if I wanted to write an equation that represented that, initial value, it didn't tell me what letters to use. I might say amount equals, it doesn't matter whatever letter I've used. The initial amount is 100. The initial amount always goes at the start. What do I want to times it by? If I want to increase it by 6% every day, I'm thinking 100% plus 6, 106%, which is the same as saying 1.06. That's an increase of 6% a day. 106% divided by 100 is times 1.06, same thing. And every day just means to the t, where t is in days. Okay? I'm always just going to raise it to whatever t, because when t is 0, it's just 100. When t is 1, it got times once. When t is 2, it got times twice. That's all it's saying. Exponential equations just meant that t is in the power. So that's the first one. Let's look at the second one. The second one, the new amount will be whatever the initial value was, 50, all right, goes at the start. What should I times by to decrease by 12%? Percent-wise, I'm thinking, well, what's 100 take off the 12%? 88%. 0.88. Okay? I hope there's some sense going in there that, okay, taking 12% off 100 is 88%. It's 0.88. If you wrote 88% there in the formula, that'll be true too. And it's always to the t. Every day, every week, whatever it's defined as, that's the exponential part of the equation. So that's us forming equations. That's probably the main bit. It's okay. Can we form an equation? Yep. We're going to use the equations too, but yes, we can form them. So which of the following be the multiplying factor for an exponential function decreasing by 99% per day? That's pretty out there, but again, don't get put off by the conversions. If you want it to drop by 99% per day, we're still comparing to 100. I'm still saying what's 100 minus that 99% you want gone every day. It means we're only leaving 1% per day. We're going to keep times by 1%, and 1% divided by 100 is that one. So the methods never change. Subtract or add to the 100, divide by 100 to make it a decimal. So what that leads us to is applied examples. Maybe population growth of people, animals, bacteria. I've already mentioned that. Yeah, we grow exponentially. Compound interest in inflation. We don't do inflation, we do compound interest. I admit I hate financial maths. Probably shouldn't, but I do. We only look at compound interest and depreciation, okay? No inflation. But we'll get to it and you'll see actually it's the exact same thing we've just been doing. Soon. A flu or computer virus, they grow exponentially. Mass of a tree trunk. You can imagine that each one of those things counts for a year, sure. But the actual mass of wood that's grown grows exponentially because each year you've got more timber growing more timber. And then you've got even more timber growing more timber. So it grows exponentially. You can see the volume in each of those circles is much more than it was in the first year or the second year or the third year. Area of a bushfire. Once again, if you've got a small fire, that fire has a certain radius, then the radius gets bigger, the radius gets bigger, it takes off exponentially because there's more fires creating more fires. And there's some population growth. That's exactly what we just did. It looks like something different, but that's just using the letter P for population. It's saying population equals initial population times some multiplying factor to some t for time. Exactly the same, no difference. Population at time t, so I want to make this formula, and then someone asks me, well, what's going to happen in 7 years? Fine, I'll chuck in t equals 7. P naught is still initial population, and m is a multiplying factor, which is maybe it's doubling, maybe it's tripling, whatever. And again, it looks like that. So let's do an example. Construct an exponential equation for a population of 16 rabbits, which is expected to double every month. The key info that I'm grabbing there is, well, I'm starting with 16 rabbits. That's my initial population. Expected to double every month. That's timesing by 2. So the population of rabbits after any sort of number of months will be the initial population times the multiplying factor to time. There's the equation already. 16 is the initial, 2 is the multiplying factor, raised to the t. And in this case, every month, all right, t's in months. Pretty version from the book, exactly that. Initial population, multiplying factor, time. So my population at any time of t months is 16 by 2 to the t. Okay, great. And again, it will graph like that. There's my 16. After 1 month, it's doubled to 32. After another month, it's doubled to 64. Then to 128. Exponential growth. So given that equation, what's the initial population of that rabbit colony, which expands at the rate p equals 5 by 3 to the t? It's 5. That's it. I've tried to overcomplicate it and trap here, but just please lock it in. The initial population is that right there. And in the parabola week, when we looked at quadratics, we said initial meant t equals 0. Same thing. I can always call it that, because when t equals 0, 5 by 3 to the 0, or 3 to the 0 is 1. I don't have to bother going through that effort. I promise you, that is the initial value. 5. Yep. For the same population of rabbits, if t is in months, how much will the population increase in any month? So after a month, which of them is correct? What's happened to the population after a month? Is it a trap, or is it just... It's just related to the multiplying factor. And what does it keep happening to it? 5 doesn't change. It keeps getting times by 3. That's it. Okay? So every formula, initial, and this number here is the multiplying factor, which just says you keep getting times by 3. For the same one again, what will the rabbit population be in 2 months? There's no trap to it. T is in months. All that's saying is what happens if t is 2? I mean, I could do it manually. If it keeps tripling every month, starts at 5, it'll triple to 15, and then 15 will triple to 45. Or just formula. 5 by 3 to the 2, which is exactly the same thing, because that means just 5 by 3 by 3. It triples to 15, and then it goes to 45. Okay, great. The formula is useful. Chuck in. Just be careful of stuff like, if that said, what will be the rabbit population in 1 year? Don't chuck in t equals 1. Just be careful of the units. The equation was defined as t's in months. So it's going to ask after a year, make sure you chuck in t equals 12 months. Okay? So just be careful on that. The formula, the t could be months, years, seconds, whatever. But it'll say it. Okay? So if you're asked to sub something in, just check. All right. Another predictable sort of question. We've got a population of a town of 10,000 people in 2016. Fine. It's expected to increase by 6% per year. We're not totally rabbit-like. We don't really double every year. But about 6% per year, okay. Construct an exponential equation for the predicted population after 2016. Now, we'll come back to that hint. If I just went from what we've been doing until now, I'm going to be totally right. I might say the new population will be, the initial population always comes first, 10,000, times a multiplying factor to the t. Well, the multiplying factor here, if it's increasing by 6% per year, that's where I think it's 100 plus 6%. In other words, I'm thinking I want to keep timesing by 106%, which is 1.06 to the t. Now note, what I've done there is exactly what the hint said. Let t be the number of years after 2016. Because what I'm doing here is saying it's like I've done an experiment, and the year 2016 is t equals 0. When t equals 1, I'm talking about 2017. When t equals 2, I'm talking about 2018. And that's the way we'll do it. I didn't want my first power to be the power of 2016. That's not how it works. I've got to raise that to the actual year since year 0, where Jesus' birthday or something. I just want to be t to the naught is the start, t to the 1 is 1 year later, t to the 2 is 2 years later. So that's exactly what we've done. So if that makes sense, perfect. Initial population, keep getting times by 1.06 for every year after 2016. So if I want the population of year 2024, all I've got to think is, well, if t is the number of years since 2016, that's 8 years later. 2024 minus 2016, that's 8 years. What's the population after 8 years? Well, it was a 10,000 initial population, and you got times by 1.06. 8 times for 8 years. So it's 10,000 times 1.06 to the 8 is 15,938 point blah, blah, blah. I don't care about decimal places, especially population. 15,938, there was a 0.4. I'm just going to write 0 dp. No decimal places, 15,938. Does it make sense? Yeah, 10,000 went up to 15,938. I'm okay with that. If it went down, I'd be worried, or if it went to 400 million, I'd be worried. But yeah, okay. You got times by 1.06 8 times. All right. What other questions we got? How many years will it take for the town's population to double that of the year 2016? Well, again, the formula we said was the population was 10,000 times a 1.06 to the t. And the question saying, how many years will it take? In other words, what time? Time's the unknown here. To double that of the year 2016. Well, 10,000 was the population of 2016. So all it's asking is, when will it be 20,000? Okay, so instead of giving me a t in this case, it's giving me the p. It's like in simple interest. Sometimes we got given the p, the r, and the n, but sometimes it told us, here's the interest. How long did it take to get there? Okay, this time you've given me the population. So the population at a certain time is 20,000 equals the initial population of 10,000 times 1.06 t. This is already what I was getting at last week. The last 2 questions on the worksheet and the last thing in the lecture was, I can't multiply those 2 things on the right. Okay? But if I want to simplify that equation, that 10,000 can be gotten rid of. Divide both sides by 10,000. That's it. So if I've got a 20,000, I'll stick in more steps than I normally would, and I'm dividing both sides by 10,000. I'm not subtracting it because it's not adding, it's multiplying. I've got to divide both sides by 10,000. What does that become on the left? 2. And that's always going to happen. If it's asking me how long does it take for a population to double, well, it got times by 2. Whatever that initial was, I just times it by 2 to put it there. So when I undo it, it's always going to be the number 2. All right, I've gotten down to this and I'm trying to work out what t is. How do I find out t? 1.06 to the t equals 2. That's not going to be pretty. What have I got to use? Logs. That's the exact situation last week that said the only way I can possibly find out what that t is if I can get it down. The only way I'm allowed to get it down is if I'm using that third log law. And this is the extent of the logs today. But yeah, I've got to take log of the left and log of the right. If left equals right, I must be allowed to write log of the left equals log of the right. Yep. And I can bring that t down the front because that was just that third law of logs that said a power can move to the front if you prefer. In this case, well, that's why we did it. So log 2 equals t by log 1.06, and the only thing left to do is get that t by itself, so let's divide both sides by this entire thing. Divide both sides by log 1.06. So the left becomes a log 2 on a log 1.06, and the right just becomes a t, and that's where I just go to the calc. I've got a log 2 equals divided by log 1.06 equals 11.9. I've rounded it a bit. It was 11.89 blah, blah, blah. So I round 11.8 up to 11.9. And I look at what was my time dealing in. Time was years. Okay, how long did it take? 11.9 years. So we've logged it up, but I had to. Okay. So it took 11.9 years to double its population. 10,000 people became 20,000 people after almost 12 years. Now the next question, how many years will it take for the town's population to double that of the year 2024? Well, in part 2, we estimated the population in 2024 was going to be 15,938. So in other words, it's saying the same formula, P equals 10. Well, actually, let's look at how long will it take for the town's population to double what it was in 2024. Let's treat it as the initial population now. Let's use 2024 as the initial situation. If I say, well, the initial population was 15,938, and you're asking me, how long will it take for 15,938 to times by 2? Well, 15,938 times 2 is equal to 31,876. So that's what I want to try and solve. That's a dot. What's my first step in solving that thing? Divide both sides by the 15,938. And what's going to happen? Same thing. The only 31,876 just came from timesing that by 2. So what's going to happen when I get that and divide it by that? It's 2. I'm exactly in the same position. All the other steps that look like, oh, where's he going to fit that? I don't have to. That is a setup for the moral of the slide being that when we worked out that it took, let's call the 11.912. When it said it took me 12 years to double population, who cares what population you started? That's going to be the law. It's going to take 12 years to double its population from wherever it is. Okay? So that's going to be a constant thing in exponential growth and decay, that it's a consistent thing. Let's look at the next page. That here we started with 10,000 people, and I've rounded to 12 years, it got to 20,000 people. After another 12 years, it will have doubled again. After another 12 years, it will have doubled again. See that trend? And that's what's happening. The doubling time of this population is just 12 years, or 11.9, call it 12 years. I don't care what population you had, on any day, it will be twice what it is now in 12 years. Okay? So the definition of doubling time is exactly that, which hopefully makes sense. The time taken for this thing to double. There it is graphed. And sure enough, every 12 years, it doubled. Doubling time. So let's look at this. Another example, this time, okay, it's a bushfire. And as soon as I look at this equation, it's telling me a few things. I don't care about sketching it, but well, clearly I do if I'm sketching it. It's not a y-axis, it's an a-axis. Okay, it's talking about the area of the fire compared to time. It says its growth, as most bushfires are. But what confirms that it's growth? The 4.2, it's greater than 1. It keeps getting times by 4.2. What's the 320? Where it starts. So here's my rough as gut sketch. I know that it's a 320 metre squared fire that gets bigger. That'll do. That's just me visualising the story. What was the initial size of the bushfire? Exactly that. The initial value is always sitting there. Again, I could have subbed in t equals 0, which turns all of that into a 1. But the initial size is 320, and don't forget its units. Its units will be given somewhere. A is measured in metres squared. Okay. So whereas if units aren't in the formula, give any answer with units in these applied things. How much area, in other words, what's A after 2 hours? I'm just going to check for traps. T is time in hours. Fine, it's just chucking in a 2. The area of a bushfire is 320 times 4.2 to the T in hours. Well, if we're talking 2 hours, 320 by 4.2 squared. That's all you're asking for. 320 by a 4.2 squared equals 5644.8. 56, instead of 44.8, 45 will do. I'm just rounding the 4 up to a 5. You wouldn't be wrong if you wrote just 5644.8, but 5645 metres squared, yep, just a substitution. Okay, so I've answered the first two. The initial was staring at us in the formula. Then we had a sub in at t equals 2. How long will it take until the fire has covered 10,000 metres squared of bushland? Looking back at the formula said A equals 320 by a 4.2 to the t. I should also say, the way I've written that, I hope that's not off-putting, there's no difference between those two things. In that one I put a times sign, in that one I put brackets. Okay? We know brackets, number hard up against a bracket is times. There's no difference, you'll see it written both ways. Okay, they're exactly the same. The reason the brackets are there are just to make it clear the 320 and the 4.2 are different numbers. But it's still a times, same thing. But we want it to have covered 10,000 metres squared of bushland. In other words, again, how long will it take? It's asking for time for when the area is 10,000. So it's a pure substitution, and I could already see it's going to be logs. It's got to be logs. If I'm trying to get an unknown that's in the power. But first things first, get rid of that 320. Don't take logs yet. Divide both sides by 320. Divide by 320, divide by 320. So it's going to get rid of it. What is 10,000? 10,000 divided by 320. It's a 31.25. Equals 4.2t. Yep, it's log time. I've got something equals something to the power. So I'm going to write log of the left equals log of the right. And here I'll say that you might have already seen from last week, if you're spotting, hang on, there's a shortcut here, this question didn't ask for working. The answer is going to be log of the left number divided by log of the right number. If you've spotted that that's just always the way it happens, if you're trying this, the answer will always be log of this over log of that. Fine, if it doesn't ask for working. But I'm just going to go to the working anyway, because that t can now come down to the front, equals t times a log 4.2, which means get rid of the log 4.2 to leave the t by itself, so both sides get divided by log of 4.2. And then I'm purely going to calc. Log of that number on screen equals divided by log 4.2 equals, and it tells me I've got a 2.398, 2.39, let's call it 2.4. I'll write 1 dp here and just check what my units of time here, and this is all about how many hours. So it started at 320 metres squared. It'll take 2.4 hours until it's covered a full 10,000 metres squared. And there's probably a part 4, but let's put that. There isn't. Okay, 10-minute break.
Yeah, it was not.
Good.
And I found that just on the ground.
Oh, cool. All right, done.
I'll do with this, how many will only will take the initial population?
No, well, I mean, you could do either. But if we're talking about double, if we're here on the same, let's look at the time since this year we'll take the double. So yeah, we'll put in the 15,928. So if in the year 2024 we started at 15,928, let's call that the initial. Yeah. Perfect.
Dave? I don't like the name of the hamburger you said. Yeah, it's a hamburger. Yeah, I know. Yeah, hamburger. He says.
Hamburger.
Yeah.
That lecture, will there be any others besides like population growth or say like the virus? Would that change? So you said it was A.
It might be.
MT, that's right.
Yeah, it's still going to look exactly the same. It might be V equals or N equals the number of bacteria. That's the only thing that's going to change. They're all going to look, even for the financials, they'll look exactly the same. Yeah.
The virus one would be like AC.
Whatever someone picked. All right, lights, that. Okay, exponential decay, it's going to be the same but backwards. There's no new tricks to it. It's got an initial value out the front. It's got a multiplying factor which just happens to be less than 1. It's going to need logs at times, so no biggie. Now, examples of it, the sort of questions will come up with and all that. Radioactivity, there's the main one. It's just the nicest one to look at, that radioactive materials decay, and they decay exponentially. So we'll get to that. Cooling temperatures, cup hot water, whatever, they decay exponentially. Depreciation, yeah, sure, we touch depreciation. We don't go into it big time, but yeah, some depreciation. Slowing of a pendulum, well, it just happens to decay exponentially. As in, if you pull the pendulum up really wide, it'll very quickly settle down. But to actually stop, it'll decay, but so slowly, hence why it's useful. Intensity of light in water, just shining a torch through water, it'll decay hugely at first. It'll block a lot of the light, but then it'll decay much slower. That I thought was interesting, fret spacing between Year 12 and Uni. I made a guitar. A lot of people have done this. That's not mine, I wish. But a 17/18 fret spacing is an example of exponential decay, that if you were going to do a guitar, bass, any stringed instrument, if you measure the distance between the nut and the headstock, we've got a 0 fret here, so you get that distance, measure it, and times it by 17/18. It'll give you a reduced length, which will be this length to the next fret. And then you measure that distance and times by 17/18, it'll give you this distance. So you can see that you keep getting, how do you space them? Well, you keep getting that length and times it by 17/18, and that's the exponential decay of fret spacing. So unfortunately our questions aren't based on that either. Radioactive decay, but absolutely. So it's the rate at which a radioactive element decays, and we often talk about half-life. Now, we just looked at doubling time, and you can, virtually they're exactly the same thing. A population of rabbits might have a doubling time. Well, let's look at the people in that 10,000 population town. The doubling time of that scenario was every 12 years your population will double. No matter what it was, it's going to be 2 times today's population in 12 years. Same thing happened, but instead of doubling life for decay, we talk about half-life. Because decaying stuff doesn't double in size, it halves in size. So the thing here is, how long will it take to halve its weight? If I've got a 60-gram radioactive rock, how long till it's 30 grams? Maybe it'll take 5 years to get to 30 grams. In another 5 years, it'll halved again. It'll only be 15 grams. In another 5 years, it'll only be 7.5. So there's these fixed times in exponential growth and decay of doubling time and half-life. Okay, so that's why we can use it. Neil should be looking. Of course, we're not going to the theory of radioactive decay. But I put it in because I was interested, because I'm not particularly a science person, I'm engineering more than science. And just how could we possibly say that dinosaurs were, 28.6 million years ago or whatever? Who's plucking 28.6 out of somewhere? And the reason we can be quite accurate in certain things is, when you find the remains of a dinosaur, when it was alive, its carbon-14 content was just totally constant. But the moment it dies, it starts to decay. And look at the half-life. 5,730 years. So the amount of carbon-14 in your system or in your remains will half every 5,730 years. So if you can measure the amount of carbon-14 content in a fossil, in an old skeleton, what have you, any ex-living being, you can calculate fairly accurately how long ago it started to decay. So that's how we can get it, half-life. So here's a typical question, and you're going to see, look, it totally mirrors what we did in exponential growth. An initial mass of 60 grams of radioactive substance is decaying by 6% per year. Construct the exponential equation for the decay of this substance. The initial letter you use, doesn't matter whether you're talking about population, use P if you want, mass, use M. I'm going to talk about, mass, that's good enough. The mass of this object is equal to what it was initially. And I don't put the units in the formula, I just note that when using this formula, my units are grams, okay? I don't write it in the formula, that just gets messy. So my initial mass is 60. What's the multiplying factor if something is decaying at 6%? Because I don't want to times it by 0.06. I want to think, instead of 100%, it's going down by 6. That's 94%, 0.94. So a reduction of 6% every year is I keep timesing by 0.94. That is 6% less than 100. Yep, so there's my 6% decay, and the only other part of the exponential equation is the exponential bit itself. Just the unknown power. T, always use T. You could N for N years, use whatever you want, it doesn't really matter. But there it is. Initial amount, multiplying factor, letter representing time. And the other thing I'm thinking, if I'm going to use this, I know my mass is in grams, and I know my time is in years. Okay, fine. What mass correct to one decimal place remains after 30 years? No trap. Let's just say sub T equals 30 into it. T was in years, it says 30 years, fine. Mass equals 60 times 0.94 to the 30. And we'll go into the calculator like that. But just remember, 0.94 to the 30 does just mean times 0.94 times 0.94 times 0.94, just decaying at 30 times. I just don't want to type it that way. I just want to type in 60 times my 0.94 to the power of 30, and it tells me we're down to 9.37 blah 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 9.37, 9.4. It only wants one decimal place, so the 3 followed by the 7 will come up. I always want to give it any applied answer, it's units, so my units are grams. And, I mean, I could write 1 dp, but I don't have to in this case. It's not like I'm telling the marker or whatever what I did. It said give it to me to 1 dp, so I don't have to rewrite it. Optional. If it just says give it and you round it, you should always state what you did. But my answer is 9.4 grams. Okay, what else you got for us? How long does it take for how long does it take for the substance to decay to 85% of its original mass? Okay, well, its original mass was 60 grams. The first thing I've got to do is dip back into either first semester memory or previous memory. My initial mass was 60 grams, and it's asked me what's 85% of 60 grams. Well, of at times in these situations, into the calculator you might use your percent key, but this is telling me 85% of 60 grams. That's how I do my calc there. That's what it's asking me. What's 85% of 60? Well, 0.85 times a 60 gives me a 51. So 85% of its initial mass is just 51 grams. So that's all the question's asking me. Now you'll see soon that I wasted a bit of time there, but it's optional. Given that the formula was m equals 60 times 0.94 to the t, and it's asking me about 51 grams, when will it be 51 grams? I replace the unknown mass with 51 is what I care about. Give me the t for that to happen. The first step is still like I was going on about last week. I can't times the 60 yet. Divide both sides by the 60. Clean it up. If I get 51 divided by 60, my number comes back again. Notice that it didn't really matter whether I used 60 and 51 or any other numbers. As long as this number was 85% of this number, it mattered. It didn't matter what the weight was. This again is like half-life. No matter what you start with, the answer to this question is going to tell you how long it will take to decay to 85% of what it was. So there's nothing wrong with doing it manually. If you see the trend and say, look, every time it does this to me, all I'm going to write is 0.85 is equal to the multiplying factor to the t, again, you are 100% correct. But if not, this method is fine. But this will always happen. If they were asking for half-life, it wouldn't be 0.85, it would be 0.5. If they're asking for how long till it's 10% of what it was, that would be 0.1. So yes, there's a shortcut, but there's nothing wrong with the way I've done it here. And there, I've got to go logs. If I want that power, I've got to write log of the left equals log of the right. That means I can bring that power down to the front, so leave the left alone. And again, I said before, there is a shortcut. If you want to go straight the answer, it's your call. But I'm just going to put the working here. Okay, so the t came to the front, and then I want the t by itself, so I'm going to divide both sides by log of 0.94. So the left stays log of 0.85, I'm dividing by a log of 0.94 equals t, which gives me the answer t equals, now the units, just want to check, I forget, was years. It doesn't tell me how to round it, so I'll write something in brackets in a sec. But log of 0.85 is equal to that number, divided by log of 0.94 is equal to 2.62, blah, 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 blah. 2.6 will do. And I'll just write 1 dp. So I'm saying it's equal to 2.6 years if I round to 1 dp. And as for what if you did 2 dp, 3 dp, whatever. Okay? 1 dp, that's fine. It takes 2.6 years. Okay, so that's that one. And chances are, I hope the second question is just what's its half-life? Okay, it's the same question, it's just instead of 0.85, it's asking about 0.5. Okay? All that working, it's exactly the same, but with a 0.85 where the 0.5 where the 0.85 was. So the half-life of the radioactive substance, again, I'll put in the extra working. If you saw the shortcut, no problem. But my equation was m equals 60 times 0.94 to the t. And if it's asking about, if it's asking about half-life, it's saying, well, if you're 60 grams, when will you halve yourself? 30. All right, 30 equals 60 by 0.94 t to the t. Divide both sides by that 60, there's that half again, I said it'll happen. Whether you write half or 0.5, whatever. I normally stick to decimals. But yep, 0.5 equals 0.94 to the t. And then, if you don't mind me skipping through and saying, look, we already did this working, and the answer will end up t equals the log of the 0.5 over the log of the 0.94, same working as the previous page, which is equal to something years, and I'll do it 1 dp again. What is it? Log of a 0.5 divided by log of a 0.94, 11.20, 11.2 will do. Again, every 11.2 years this thing will halve its mass. So there's the concept of why is radioactive waste such an issue. Well, if this thing started at 60 grams and kept halving itself every 11.2 years, in 11 years it'll be 30 grams. After 22 years it'll be 15 grams. Then after 33 years it'll be 7.5. After 44, what's the problem? Never gets to 0. Okay, it keeps halving itself, but it doesn't disappear. We're stuck with it. So it might get tiny, but we're stuck with it for a long time, especially if it takes 5,730 years or something like that to halve itself. We're stuck with radioactive waste for a long time. So there's our concept. Now, okay. This is just testing that we understand what half-life means. And when you look at half-life, remember life, it's a time. Okay, it's not saying what's mass. Half-life just means how long until you halve yourself. Now look at that thing, it says mass equals 200 times a half to the t. So initially I'm picturing this thing. Again, we don't have to sketch them, but I like to just picture in my head mass versus time. It's starting at 200 and it's clearly going downhill. Can anyone see that? I'll get rid of D. There is enough info there to answer this question. What its half-life is. How long will it take for this thing to halve itself? Let's put in a few points. What mass will it be after 1 day? If it's 200 and it keeps getting halved every day, we've already answered it. It halves every day. So the half-life question says, how long will it take for it to halve itself? 1 day. Every day it halves itself. After 1 more day, it'll only be 50 grams. Okay? It'll only be 25 grams after another half. So that thing, just because it happened to be a half in there, halved itself every day. So that was just a check on the concept. I started at 200, and every day goes by I halve myself. Its definition is half-life is 1 day. So, again, I'm playing with that concept. Given that the half-life of davrochium is 1 year, and my sample weighs 400 grams, how much will this weigh in 3 years? If it's got a half-life of 1 year. No formulas, just concepts. So the half-life is 1 year. Every 1 year it halves itself. So here's t equals 0. Here's today. I've got a 400 gram thing. 1 year, 2 years, 3 years. What's its weight in 1 year? At the end of the second year? In the third year? Yep. Okay? There's the concept of half-life. If it said 1 year, it doesn't have to be 1 year, but if it says my half-life is 1 year, every tick of every year that goes by, I halved. What about this one? Benderpium has a half-life of only 4 months. And my sample weighs 120 grams. Ben's got to give this lecture on Wednesday. He'll enjoy that. Every 4 months. Okay, it's nice to lock in every 1 year. Nope. Every 4 months, this sample will halve in mass. How much will it weigh in a year? in 1 year, in 4 months, it will have halved itself. 120 has gone to 60. In another 4 months, 8 months total, it's halved itself again. In another 4 months, it was actually the same as the last question. It halved itself 3 times because there were 3 4-month intervals in a year. So it got itself down to 15 grams. Okay. All right, another half-life one. Find the half-life. Does it sound like a predictable question? Probably written. Week 9 quiz. Yeah. Find the half-life of a radioactive substance which decays according to that. M is grams, C in days, perfect question. Again, I can see you started at 200 grams, you kept getting times by 0.8, yes, your decay. What do I really care? How long did it take for you to halve your mass to 100? So instead of M equals that, I want to know how long it took before this 200 became only 100. And I know that that's just the times there. That's what I'm solving. I can't do that times yet. Predictable as hell. We divide both sides by 200. 100 on 200 is just a half, fraction, decimal, whatever you want to call it. All half-life questions come down to a half equals something to the t. And log it. Log of the left is log of the right. That log of the right, that power is allowed to come down to the front now and multiply the log 0.8. I want the t by itself, so I'm going to divide by a log 0.8, divide both sides by a log 0.8. On the left I've got a log 0.5 and a log 0.8. On the right I'm just left with the t. It didn't tell me what to round it to. T is in days, I'm just going to make sure I write that. Whatever, I don't know. Log of a 0.5 is equal to, divided by log of a 0.8 is equal to 3.106 for 3.10, 3.1 will do to 1 dp. If every day, if every 3 days it halves itself, fine. Hopefully it made sense of that. Half-life or doubling time, same question, and the log content, repetitive. So, the next one, all I'm leading here to is another question. Newton's law of cooling, he came up with this, but look at it, it's exactly the same. It's a fraud. The temperature of the cup of tea, say, is equal to its initial temperature times some number to the t. Same thing. Initial temperature, multiplying factor, it's exponential decay. So, here's just a question, and it's just got a slight twist. The only reason I've included this question in there, and Sheldon, is there's a slight twist to it. I have been doing this, I promise you, this number out the front is the initial value. So, unless I'm a liar, 78 should be the answer. But I lie sometimes. Why is this different? That. Okay? So it's only because it's got that. None of the questions until now have had that. This question has a plus 22. I can't just ignore it. And the initial temperature of the hot tea is just when t equals 0. So I do have to, sure, 78 is the initial value of this thing, but if you've got a plus 22 in the end, it's part of the formula. I've got to add 22 to it. Literally, the t equals 0 just tells me 0.82 to the 0. And 0.82 to the 0 is just 1. Anything to the 0 is 1. So my answer is 78 plus 22. So that's what his studies were on. I had a thing of water brought to the boil. So please don't think I'm overall a liar. The number at the front is still initial value, but if you've got a plus function on the end, it just means chuck that onto any answer you've gotten. Because this thing here is not doing that. All these exponential things, we're going from some temperature, like if I just plotted this part, it'd be 78 approaching 0. But if I had a cup of hot water here, would it approach 0? Maybe this room is 22 degrees Celsius, and it'll approach 22. Okay? So that's why there's a plus 22. And again, we don't have to sketch it. I like seeing it. And what I'm saying here is, it's at 100, but it's approaching 22 degrees, because it's not going to go below room temperature. You know, any hot fluid in here, or if I had a glass of ice, they're going to approach whatever their room temperature is. So, when will the tea's temperature reach 25 degrees Celsius? It's the same as all the other questions. I can't ignore the plus 22, but I reckon we can handle it. It's asking when means find T, when the big T is 25. All right, we're subbing in the big T. And again, I do change these things to times. What would be the first thing to do in this scenario? Just algebra stuff. The easiest thing to do here is minus that 22. Okay? Before, if that plus 22 wasn't there, I'd be saying divide both sides by 78. But rules of algebra were get rid of the easy things first. Subtracting 22 from both sides is definitely the nicest thing to do here. So that becomes a 3 equals 78 times a 0.82 to the t. Then I'm back to a few slides ago and say my next move is to divide by 78. Now probably 3 divided by 78 is probably horrible. Yeah, it is. So I'm just going to leave it as a fraction. If you wanted to approximate it, you could write 0.03846. Fine, a little bit of rounding error. It's not going to kill us. But I'm just going to leave it as 3 on 78. And fine, I've got to log it. All right, I'll log it. Log of the left, it just happens to be 3/78 equals log of the right. That t can come to the front. If you're getting deja vu, you should be. And then the next step was always divide by that log 0.82. So on the left, I've got a log 3 on 78. It's getting divided by a log 0.82. And again, I'm going to remind myself, what was t in? Was this minutes? After t minutes, it was given in the formula. So I'm about to get an answer in minutes. The log bracket 3 divided by 78 bracket is equal to that, divided by log of 0.82. Gives me a 16.41 blah blah blah, 16.4 minutes. Okay. It takes 16.4 minutes to get down to 25 degrees Celsius. Same, just the minor twist of the plus 22, but we're on top of it. And again, the minutes. Don't forget to just stick whatever the units were. Go check the question again. Put the units in. Next one. Will the temperature reach 22 degrees Celsius? I should have written. This one's a physics question. We're not going to get asked this. Does anyone have an opinion anyway? Theoretically, mathematically, no. Real life, yes. Okay. This room wouldn't be precisely 22.00000 degrees. I mean, the graph would look like that, forever approaching, but never touching 22, theoretically. But in real life, the room will be changing. It'll get to room temperature, okay? We're not in this perfect vacuum and all that. But let's just speak mathematically. No, it'll forever approach and never touch it, okay? But anyway, that's just the concept. I just want to show that graph that was the same as every other graph. It just got pushed up 22. Okay, here another good predictable question. Find the doubling time of a population according to some equation. Well, I can't read it straight off, but again, doubling time is just saying twice what it was. The initial population here is a 24. I can't be asked to find half-life here because it's not reducing, but I can get asked to find doubling time. It's getting bigger, and what I'm really interested in, if it started at 24, the question is saying when's at 48. So I just grab 48 from 2 times the initial value, which is sitting out the front. Again, predictably, when I get rid of that 24, it's the number 2. So doubling time is 2 equals something to the t. Half-life would be half equals something to t, and so on. And then it really does get ridiculous. I'm doing this thing again. Yes, I'm bringing down the t. I'm going to stop doing these soon. And yes, I'm dividing both sides. And t equals the answer to that, which is a log 2 divided by log 1.2 equals, t is in months, fine. So I've got a 3.8 answer. It was only followed by a 0. I want months, and I just did 1 DP again. Okay. Hopefully that's about the end of them. I think we've covered and repeated. Good. Okay. Well, not good, because now it's money stuff, but it's exactly the same. And you don't have to use the formulas for this financial stuff. There's all different ways they write the formulas. I don't like the formula. I like to just do exactly what we've just been doing. There's an initial amount, there's a multiplying factor, and there's a t. But it's your call. The formula's there to use. So firstly, compound interest we'll look at definitely. Now, we've done simple interest, which isn't real life. It's just this gross generalisation saying you'll get about this. Really what happens is, of course, I think they do it daily. At the end of today in my account, they'll calculate the amount of interest I've earned as 0.00032 cents, and they'll add it into my account. And then tomorrow that interest will be on a bigger amount by 0.00032 cents. But an example here. Yes, we had simple interest and it was just straightforward. But as I said, in reality, this is what happens. So whereas this is a very simplistic example, Neil should be watching because this is just an intro to the formula. And really we've done the formula. But if I put $100 in at 10% per annum, good luck with that, compounded yearly for 4 years. Again, we compound more often than that, but let's just pretend we only calculate at the end of the year. I'll put in $100, 10% of that is $10. So at the end of the year, I've got $110 in the bank. Why is compound interest so good? Because in the second year, simple interest would have just said $100 times 10% and still make another $10. In compound interest, it says, no, you've got $110 in the account. 10% of that is $11, so you've made interest on last year's interest. So now you've got $121 in your bank. Well, that's the start of your next year, which gets $12.10 in interest. So you can see, instead of only being $40 interest in simple interest, if we compound yearly, I got up to these values. What are they up to? Oh, you'll think I'd add them up on there. I didn't even add them up. Okay, $46.41. So I made $6.41 extra. Okay. Now, instead of these steps, we don't want to do this manually, we just want a formula. If we look at the formula, the amount of interest I made in that first year was my initial value, which always goes at the front, and it got times by 1.1. That's a multiplication factor for increasing by 10%. 110%, that's 1.1, which is the same as writing my principal amount times 1 plus the rate of increase, 10%, 0.1. Then what we did was we times it by 1.1 twice. The initial amount got times by 1.1 twice, so it's the same as principal times 1 plus r squared. So you can see the formula happening here. We end up with that formula. What I really want to say is you can use that for all of today's lecture if you want, or you can ignore it. But what does that formula say? It says your new amount of whatever, dollars in this case, is equal to your initial amount, as it always was, times the multiplication factor, which is 1 plus whatever it's increasing by. In interest, we're only talking about increasing. I don't care about taking stuff off it. This isn't depreciation yet. I'm only increasing to n, where n is the number of times. That's exactly the same formula. Initial amount times multiplying factor to some letter representing t. So, note that, maths world uses this. In the financial world, they use future value of an investment and present value of an investment. But they're the same formula, aren't they? It doesn't matter what letters we choose to define these things as. It doesn't matter. I'm going to use this formula just because it's the accepted maths way. You can use whatever you want. So here's an example, and there initially is just an example. Well, if we're compounding yearly, is it different to compounding monthly and so on? Absolutely. The more often you compound, the more money you get. If we were to calculate it monthly, I'd make more money than calculating yearly, because sooner I'll be making interest on my interest. So if we were looking at how much compound interest will be earned on $1,000 at 5 years at 8% per annum compounded, well, if we compounded yearly, there's my formula. My principal amount is $1,000. My rate is 8% per annum, which means per year, doesn't need adjustment. And the number of years is 5 years. chuck it all into the formula. My multiplying factor is 1.08 to the 5 years. Okay, my $1,000 becomes that. 2 points, I want to separate this from simple interest here. Remember the simple interest formula calculated your interest. This does it. This calculates your final amount in the account. So your initial amount of $1,000 is still in the answer. So just note the question. If it says, how much interest will I earn? My answer is $469.33. Take the initial amount off. If it says, how much is in my account now? That's your answer. So simple interest only calculates interest. This one calculates the total in your account. The other key difference is in simple interest, we were able to decide, do I want to convert the percent or do I want to convert years to quarters or quarters to years or whatever? It didn't matter what we did. Here it matters. Whatever you're compounding, however often you're compounding, if we're compounding yearly, everything must be in years. Compounding monthly, everything's per month. So in this question, it had to be per year, correct, number of years, correct. In the next question, if it says half yearly, I need to know my interest per half year. I need to know my number of half years. Well, the principal amount is still $1,000. If it's 8% per year, it's going to be 4% per half year. If I've got 5 years, that's 10 half years. Stick it all in. And what was the last one? The last one was 1469. Now we've made more interest at 1480. We made $11 extra. What if I brought it down to quarterly? I know this is already in the notes, so I don't want to go through that slowly. But I'll divide the rate of interest by 4. If it's 8% per year, it's only 2% per quarter. And if it's 5 years and every year contains 4 quarters, it's 5 fours, that's 20 quarters. Stick it all in and we're up to 1485. That was roughly another $5 interest. If it was monthly, well, I'd get my yearly interest rate and divide by 12. And I'd get my number of years and times by 12. 5 times 12 months, that's 60 months. So again, I've converted everything to months. Go in and I'm up to 1489, so another $4 or so. If I did it daily, well, we don't really bother with that. If we did, I'll just reiterate, how many days per year to use, because it depends what year you're talking. But let's just talk about 365. So I got my interest rate divided by 365. I got my number of years times 365, and we got another couple of bucks interest. So there's the comparison. Clearly, the more often we compounded it, the more money we made. All right, there's the background. There's the feel-good bit. What do we have to do? Right there. There's a typical question for us. Again, if you use that formula, great. If you don't care, fine. If I use the formula, I'm just going to look at any compound interest question and say the amount of money this investment's going to be worth is the principal amount times 1 plus R to the N. The principal amount here is $2,000. Now I'm going to search for compounding monthly compounding. So not picking on that month, just wherever it says. It's got to say somewhere how often it's compounding. That's my key word. If it says monthly compounding, I want everything in months. So 2% interest per month, that's cool, but 3 years has got to convert. I want everything in months. So instead of 3 years, I'm going to call it 36 months. Okay? Every year's got 12 months. So 36 months, 2% per month, gold, in it goes. 1 plus, my rate is 2%, which is a 0.02, to the 36. Now I'll admit, if I was using the previous bit of the lecture, I would have said my new amount is equal to the initial amount, times, if I'm going up by 2%, that's 1.02 to the 36. Well, it's the same, isn't it? I did that in my head, the 1 plus the 0.02. This formula tells me exactly what to do. Who cares? Your call. Either way, I'm taking the same thing in the calculator, 2,000 times a 1.02 to the 36, and it says it's worth 4,079.77. That last 7 was followed by a 4, so I didn't take it up. That was dollars. I'll write 2DP there, nearest cent, whatever you want. Clearly that's a natural thing to do with dollars, 2DP, dollars and cents. Now let's check, did I answer the question? Find the final value? I did. Didn't ask me how much interest did I make. Said what's the final value? If I put $2,000 in, it'll end up with a final value of $4,079.77. Yep, all good. Okay, so what was the key thing? Circle your compounding period, convert everything to that, and we're sweet. So what's the next one asked for? I'm circling compounding quarterly. Now, quarterly can cause issues. It doesn't have to. We know it's a factor of 4. The word quarters telling us that. I know my principal amount is there. Principal doesn't need converting, it's just an amount. 1.5 years. How many quarters is that? It's 4 quarters in a year. A half year must have 2 quarters. It's 6 quarters all up. And we were right, it was a factor of 4. 1.5 times 4 is 6. Okay? If it's 8% interest per annum, will it be more or less per quarter? It's got to be less. You'll get 8% if you leave it in the whole year, but per quarter, you'll only get a quarter of that. So it's 1.5 times 4 is 6 quarters. 8% divided by 4 is 2% per quarter. I just divided it by 4. Okay? Over a year I'll get 8, but only over a quarter I'll get 2. So that's going into my formula. The final value of an investment, no trap in the question, equals, well, the principal amount is $300. Then it says 1 plus R. Well, I'll write it that way. The rate is 2% to the power of the number of terms. In other words, you may have gone straight to, it's your decision. That's the line I'm more comfortable with. 300 initial, it's going up times 1.02, 6 times. 300 times 1.02 to the 6 is a 337.848. 337.848. The 4 is followed by an 8. Up it goes. Dollars, TDP. That's the following. I started with $300, ended with $337. That's what the question asked. Happy. Okay, I know I'm running short on time. Okay, how much should Sarah put in the bank now? The question's changed, like simple interest did. It's not giving me the P, it's asking me for the P. The P is the amount you put in the bank. So here's the formula. A equals P, 1 plus R to the N. It's saying she wants to have $1,200 total investment. That's the A. The P is going to be something less. Maybe P is 800 or something. How much does she need to put in the bank now? So it's going to be worth 1,200. Well, compounded quarterly, what a pain. I've just got to convert things to quarters. It was 4% per annum, so it's only going to be a quarter of that. 4% per annum is 1% per quarter. And 2 years, how many quarters in 2 years? Times 4. 4 in that year, 4 in that year. Instead of 2 years' time, I'm going for 8 quarters. All right, so 1,200 equals P, 1 plus 1%, which is a 0.01, to the 8. Again, I don't like that line, but no. 1 plus 1.8. There's my happy place. 1,200 equals P times 1.01 to the 8. Up at 1%, 8 times. How do I get to the P? It's being times by 1.01 to the 8. Let's divide by 1.01 to the 8. I don't need to go to the calc yet, probably not pretty. But if I divide both sides by the entire thing I'm trying to get rid of, 1.01 to the 8, once it's done, I don't need to bracket it. There's nothing left to do in the brackets. You see, all I've done is divide by 1.01 to the 8. So 1,200 divided by 1.01 to the 8 gives me 110818. Yes, it's dollars. Yes, it's 2DP. Okay, so that's not too spectacular. Not have 1,200, should still have to invest 1108. It's the right direction. You know, clearly it had to be less than, but yeah, 2 years at 4% doesn't make you that much. Okay. I hate these already. How long will Bryce have to invest $2,000 for at 8% per annum compounded yearly if he wants to increase to $4,000? What's the key issue here, and why would this be worth double the marks of other questions? It's finding time. How long? This is a log question. It doesn't exactly announce it, but let's sub in. Now let's also check compounded yearly, 8% per annum. Good. I don't have to convert. That's something. Everything's in years. My formula said the final amount of investment is equal to P times 1 plus R to the N. Well, I want my principal of 2,000 to become 4,000. So that's my A and my P. Put in 2,000. How long till I can dig out 4,000? So there's no other trap. It's not a subtraction. It's just put in 2,000, take out 4,000. It's a doubling time question. 1 plus a rate of 8% per annum to the N, where the N's the unknown. Let's simplify it a bit. Let's divide both sides by 2,000. Like I said, it's a doubling time question. There it is. 4,000 or 2,000 is the number 2. I've got a 1.08 to the N. Forgive me if I just write that and then go to the final answer, because we're at the same spot as every other question now, aren't we? The N comes to the front, we divide that, and N is going to end up being log 2 over log 1.08. It's going to be in years because we're compounding yearly. It's something years, and the something is a log 2 divided by log 1.08 equals 9.00. Okay, it's 9 years. All right. Last bit. Oh, how long would it take for 3,000 to become 6,000? Well, look what we just answered. The doubling time of this money was 9 years. It went from 2,000 to 4,000 in 9 years. How long will it take to get from 3,000 to 6,000? 9 years. It's an exponential thing. It'll take 9 years to double. No matter what you started at, this thing doubles in 9 years. So it's the same answer. Depreciation, I'm not interested in the words, blah, blah, blah. What's the difference in depreciation? There's a minus, because it's going down. That's it, okay? And I'll write this out because we're here. Depreciation is all done yearly. So depreciation is actually really nice. We're not bothering with the quarters and that. Our depreciation rules as per tax is just yearly. So if my formula is exactly the same, but it's depreciation, so I'm taking the rate off the 1, what would be the depreciated value is the new value. The principal value of this computer was $3,000. It's 1 minus a rate of 25%, which is 0.25, to 3 years. So note, everything will be per years for depreciation, which makes it a pretty nice question. It's 3,000 times a 0.75 cubed, because the 1 minus 0.25 is a 0.75. So 3,000 times 0.75 cubed has got me down to a depreciated value of 1265.63. To 2dp. Straight subbing into the equation. Again, sorry, I'm speeding this up at the end. I'll make sure I get it on the recording. So the depreciated value becomes out after 3 years. And the second part was how long will it take the value to reduce to half the present amount? It's half-life. What's the half-life of a computer? The same question, it's just if A equals P, 1 minus R to the N, instead of the initial 3,000, we want it to halve to be worth only 1,500. It's still 1 minus a rate. 1 minus 0.25 is still 0.75. That's my question. And when I divide both sides by that 3,000, look, it's exactly the same as every other half-life question. A half equals the multiplying factor to a power. And if I take logs of both sides, again, apologies for the shortcut, I know I'm going to get a log half and a log 0.75. I know it's going to be in years, and I know it's going to be log 0.5 equals divided by log 0.75 equals 2.4 years. Made it. All right. Hope it was enjoyable. More hamburgers you want? More hamburgers. Okay. Can do. Yeah.
Hey Dave, so do we not have a quiz next week?
No quiz. No tute, no quiz, just this and then start your holidays over.
Are you still doing the Tuesday 9 to 10? Or do we have the other guy permanently?
Permanently.
Okay.
Yeah, we had to do a swap because we had to swap, so I took his 11 or 12 instead.
Okay.
Yep. So, yeah, and still, yeah. So say he's in the same room, LG 59.
Yeah, yeah.
But yeah.
Yeah, okay. Thank you.
All good?
Yeah.
Okay.